Electricity guided man into space and gave him the power to move mountains. It extended his ability to communicate and to calculate. Electricity has become indispensable to industry and commonplace in our homes. The electrical force of nature, mysterious and unpredictable until a century ago. Then man observed certain fundamental characteristics and established basic principles. Electricity was tamed and put to use, turning night into day. It was harnessed to power machines, and it accelerated the pace of the 20th century. Electricity guided man into space and gave him the power to move mountains. It extended his ability to communicate and to calculate. In less than a century, electricity has become indispensable to industry and commonplace in our homes. And no longer is it thought of as an unpredictable force. Today we still know little of its nature, although we have found that electricity behaves in a constant and predictable manner. The most accepted theory is that it is comprised of moving electrons. To understand this theory, let's investigate this world of the electron. Let's look inside one of nature's elements, for here is where we will find the mysterious force of electricity. We reduce an element to its purest and smallest form, the atom, and find the world so minute it is beyond imagination. This atom is about 1/100 millionth of an inch in diameter. Circling around the atom's relatively heavy nucleus are small electrically charged particles called electrons. But because it is not practical to show the correct relative proportions of an atom, we represent the atomic structure with a symbol. We can think of the atom as a group of relatively light particles arranged around a heavy nucleus. The lighter electrons carry negative electric charges, and the heavier nucleus carries positive charges. Normally, a state of balance is maintained within the atom. The positive charges in the nucleus equal the negative charges of the electrons. When these charges are equal, the atom is in electrical balance, or in a neutral electrical condition. It is possible, however, to disturb this normal balance, whereupon the unbalanced atom assumes an electrical charge. Too many electrons will produce a negative charge. Too few will throw the balance to the positive side. Thus far, we have been concerned with the electrons of individual atoms. Now, let's see what can happen when two neutral atoms come together. The outside electrons will no longer move exclusively about their original atoms, but will circulate about both atoms. If many atoms are close together, as those in a piece of copper, a few of the electrons can detach themselves from their original atoms and move freely throughout the metal. However, as long as the entire piece still retains its normal number of electrons, it is electrically neutral. But like an individual atom, the metal also can lose some of its electrons and become positively charged. Or it can pick up more than its normal number of electrons to become negatively charged. Electrons always try to move from a negatively charged body to one that is more positively charged. If two objects are brought into contact, the electrons will flow from one to the other until both are equally charged. The establishment of unbalanced charges in matter is an important principle in the generation of electricity. A wet cell is a practical source of electric energy which utilizes this simple principle. Zinc metal is suspended in a suitable container. Its atoms are neutral until a dilute acid solution is added. Then, some of the zinc atoms dissolve into the solution, leaving a few of their electrons behind in the metal. This gives the zinc metal a strong negative charge. Now, a piece of copper is put into an acid solution in another container. Fewer copper atoms go into solution, so its metal becomes only slightly negative. And since the copper has the weaker negative charge, it is positive in relation to the zinc. If we now combine the solutions, the charges in the mixed solution will become equalized, but the metals, or terminals, will remain charged. We now have an unbalanced condition of the electrons in the metals, which can produce a continuous flow of useful electric current. All work performed by electricity requires a flow of current, or movement of electrons. So let's see what principles are involved when current flows. There are three related factors that affect the flow of electricity: electric pressure, or voltage, electron flow, or current, and opposition to electron flow, or resistance. First, let us consider electrical pressure, or the voltage. With nature always trying to maintain an electrical balance, there is a tendency for any negatively charged object to throw off or repel its excess electrons, and for a positively charged object to attract electrons. This urge to maintain an electrical balance is the source of electrical pressure. And since this electrical pressure is a repelling and attracting urge caused by opposite charges, its force, or pressure, is equal to the difference in the charges. It is therefore called the potential difference. The unit of electrical pressure, or potential difference, is the volt. The voltage, then, represents the sum of the extra electrons at the negative terminal and the deficiency of electrons at the positive terminal. When a suitable path is provided, the voltage causes the electrons or current to flow from one terminal through the path to the other terminal. To better understand current, let's review the action of the atoms and their electrons in a piece of metal where we saw swarms of electrons moving freely in all directions about the atoms. If an outside electric pressure or voltage is applied to the metal, the electrons will move predominantly in one direction. The effect is that the electrons move from the negative to the positive terminal. This effect is electric current. Let us now consider the unit of electric current, the ampere. 1 ampere represents, now hold on to your hat, 6,300,000,000,000,000,000,000,000,000,000,000,000,000,000,000 electrons passing any given point in 1 second. The electron flow, or current, then, is the number of electrons that pass a given point in a given time. And now the third factor, resistance. This factor depends on the nature of the material through which the electrons flow. Going back to the motion of electrons in a metal, we saw that many unbound electrons moved freely about and among the atoms. Substances in which this takes place are good conductors of electricity. However, even in the best of conductors, some of the electrons collide with the atoms, which tends to retard the movement of electrons. These collisions are the cause of electrical resistance. In some metals, collisions are more probable than in others. Therefore, different metals offer different degrees of resistance to the flow of electrons. For example, Copper has low resistance because it permits the electrons to flow freely with few collisions. It is considered a good conductor. Iron offers more resistance than copper. Collisions with the atoms are more frequent. Therefore, its conductivity is less than that of copper. In some substances, no electrons are free to move around as they are in most metals. All of the electrons are bound to stay with their atoms so that no current can flow. Substances like these, glass, porcelain, rubber, plastic, are poor conductors. But because they allow little or no electron flow, they are useful as electrical insulators. On the other hand, in some metals, the resistance to the flow of electrons is put to good advantage. The collisions of the electrons set the atoms into violent vibration, making the metal hot. If there are enough of these collisions, the metal will radiate heat and even light, as in an incandescent lamp, a direct result of a metal's resistance to the flow of electrons. The unit of measure of this resistance is the ohm. Its value is best understood when it is related to the volt and the ampere. In the relationship, a pressure of 1 volt produces a current of 1 ampere through a resistance of 1 ohm. Ohm's law expresses this relationship as a constant proportion. I equals E over R. I is the intensity of the current in amperes. E, the potential difference in volts. And R, the resistance in ohms. Another important relationship between voltage and current is P equals E times I. P, the unit of electric power, is expressed in watts and equals the voltage times the current. Whatever the source or the magnitude of electric energy, these factors have the same relationship to each other. Today, our cities and industries require great quantities of electric power. Large electric currents at high voltages are conducted over long power lines, so electricity can power industry, transport our growing population, light our streets, heat or cool our homes. But where is the source of this power which seems unlimited? The major source of electric power is the electromagnetic turbine generator. This giant power maker converts the mechanical energy of steam-driven turbines into electricity. But to understand how electric power is generated, we must first look into the nature of magnetism. For the same basic laws which govern the electromagnetic generation of electricity are apparent in a single magnet. Magnetism, like electricity, is a mysterious force. We don't know exactly what it is, but we can observe its behavior and formulate basic laws. We know that the Earth itself is a magnet and the needle of a compass, and so are minute particles in a piece of iron, which are called domains. And we've found that when a predominant number of these domains point in the same direction, the bar itself becomes a magnet and has a magnetic field. Also, we can easily demonstrate one important principle. Material which can be attracted by a magnet can become a magnet. All material of this nature is made up of tiny magnetic domains. However, some materials, such as copper, have no magnetic domains. These materials are non-magnetic and cannot be magnetized. In addition, we know that every magnet has a magnetic field, and magnets may be made in various shapes to provide convenient and strong fields. To understand how a magnetic field is useful in the generation of electricity, let's again look at the electron, Mr. Electron, and watch him move across the magnetic field. Let's watch him again. Notice, as Mr. Electron enters the magnetic field, he is deflected from his original course. This deflection depends upon his velocity and the strength of the magnetic field. Previously, we have seen that conductors have many free electrons. Therefore, if a conductor is moved across a magnetic field, the mechanical action of moving the wire causes these free electrons in the wire to be deflected, just as we saw Mr. Electron deflected. This flow, in effect, establishes a negative and a positive charge at the ends of the conductor. And we now have two charged terminals capable of producing a continuous flow of electric current, just as we had in the wet cell. In practice, a means of continuing the movement of a conductor within a magnetic field is provided. The operation of all electromagnetic generators, regardless of size, is based upon this simple principle. Electrons are deflected in a conductor moving across a magnetic field. In the steam turbine generator, water is heated and converted into steam, which expands and rotates the turbine wheel. This rotation provides the movement necessary to deflect electrons in the magnetic field of the generator, and electricity is produced continuously. But now we must make electricity perform useful work. So motors are connected to this convenient source of power. They convert electricity back into mechanical energy. In doing so, the magnetic principles again apply. Remember that an electron moving across a magnetic field is deflected. If the electron were moving in a wire, as when electric current flows, the deflection of the electron would cause it to push against the wire, tending to move it. Billions upon billions of these tiny pushes combine to provide a strong force. The larger the current, or the greater the number of electrons, the greater the force moving the wire. These forces on current-carrying wires in magnetic fields furnish the power for all electric motors. And in all motors, the principle is the same, from the smallest to the most complex. Magnetic fields deflect electrons flowing in current-carrying wire. This deflection produces a force. In fact, this principle, the interaction between the magnetic field and electrons, is the basis of all electrical machinery. Let us review the fundamentals of electricity. The billions and billions of atoms of which the universe is built are composed of positive and negative electric charges. These charges are normally balanced in matter. By unbalancing them, electric energy is made available. And the urge of nature to restore this balance creates electric pressure. The response to this urge, nature's action to restore the balance, is a flow of electric current. Electric current, then, is simply the movement of electrons away from objects that acquire a negative charge to objects whose charge is relatively positive. The three related factors that affect the flow of electricity are pressure, measured in volts, current intensity, measured in amperes, and resistance, measured in ohms. Whatever the source or the magnitude of electric energy, these factors have the same relationship to each other. These are the simple principles that make possible all of our electrical servants, servants that contribute to our comfort, safety, and convenience. These principles are the laws with which man understands and controls the power of progress. Yesterday, today, and tomorrow.